Um, so finally, I'd like to introduce our speaker of today, Joshua Loftus. Joshua's research focuses on improving practices in data science and machine learning, in particular reducing biases associated with social harms and scientific reproducibility. His work includes developing methods and software for statistical inference after model selection and using causality to analyze the fairness and interpretability of algorithms in machine learning and artificial intelligence. Joshua earned his PhD in statistics from Stanford, was a research fellow at the Alan Turing Institute and the University of Cambridge, was an assistant professor at NYU from 2017, and he recently, lost for NYU, joined the London School of Economics. And Joshua is going to talk today about racial biases in artificial and intelligence and data science. Joshua.
Thank you, Weiji, and thank you to all of the organizers and participants in this really worthwhile workshop. I've enjoyed all of the previous talks and learned from them, and I really hope that that everyone here will find value in what I've prepared. I'm happy to continue the conversation, after the workshop, if people want to contact me about any of the things that I talk about today as well. So I'll start by, even though I know that many of us are probably already familiar with things like deep learning, I'll start with a very kind of introductory overview of AI, because I think it's really important for everyone to view it as something that's accessible and really just another tool that people can use, rather than as something that has kind of mystic properties and can magically solve our problems or things like that. Then I'll talk about several examples of racial biases in certain AI applications, and then I'll talk about some of the ways that we can try to start fixing some of these systemic problems. So yeah, this might be one of the most controversial things that I say here. What is AI? It's regression. So AI, it has a lot in common with machine learning, which has a lot in common with regression. If you're familiar with regression, that's a really useful way to think about what these other methods are doing. They're just kind of regression with bells and whistles. The idea is you're just going to fit a function that by combining some data with an algorithm. So you have a data set, you have an algorithm that inputs that data set, and out of this you get a function, and that function can tell you predictions for something. So one of the things about AI that makes it a little different from regression is that AI is usually considered too complex for humans to really understand the function that you create when you fit an AI. And so as a result, we typically only have kind of one way to evaluate AI applications, and that is to look at the performance of their output. So the idea is that the computer learns some type of function, and that function might be very complicated, too complicated for us to really visualize or understand all of its intricacies, but we can look at the output of that function. And so that's kind of the one way that we typically approach trying to understand what an AI does. So like machine learning, AI, regression, all of them have this input of a data set. So AI typically requires large data sets that have many examples, and it usually needs many examples that are similar to the type of data that you want a prediction for. So for example, there are a lot of AI applications that do image recognition. And so the data here could be a lot of images, and you might want an algorithm that can tell you if this image has a cat in it. So you'll need a lot of images that have cats in them, and you'll need a lot of images that don't have cats in them, so that the algorithm can learn the difference between those kinds of images. And the input might be something that we could understand, like an image. What the computer does with that input, that's something that might be very complicated. But then the output might be something like, an answer, a yes or no answer. Yes, this image contains a cat, or I have a certain sort of confidence about how confident I am that this image contains a cat, something like that. And so images are a really useful example in AI because we tend to be pretty visual learners a lot of the time. But AI doesn't only involve image applications. You can have data that comes from text or other types of formats as well. And that's kind of one of the things that's relatively new about the current phase of AI research, is that more kinds of things are becoming data. So images as data and text as data, that's kind of increasing trend over time. So there's a continuous history in unfolding that AI is just the most recent iteration of, and it's useful to keep the context of that history in mind. I find it useful to learn a bit about the history of things in order to understand those things. So I'll say just a little bit about some of these kind of classic methods like regression and decision trees, just so that we can use them as a sort of contrast for what some of the more modern AI applications do. And then there's a lot of things that are new about AI, but there's also a lot of things that really aren't so new. This is a still from the film Modern Times. This is Charlie Chaplin. He's been kind of sucked into the machine, and this is a film from 1936. And when you think about what a lot of AI applications are now doing in systems that involve a lot of people, like an Amazon fulfillment center, where a lot of workers are being kind of allocated and told where to go in the warehouse by an AI. This is, well, I guess the left example is not a real is a comedy, but there's some aspects of this which are not so new. So I want to say a little bit about what's not so new. AI it inherits from technology, particularly information technology. AI applications, especially the kinds that we'll talk about today, are embedded in social and economic systems. So they inherit all of the issues associated with these. And, history, like we didn't suddenly escape history by inventing this new technology. So in particular, AI comes with a lot of issues. You wouldn't say that all technology is always good, and you also wouldn't say that it's always bad, right? It's a tool, and it depends on the way we use it. It depends who's using it and for what. This is a picture of the Fukushima nuclear meltdown. Nuclear technology has a lot of promise, but it also has to be done very carefully for it to be safe. I think of AI that's a good analogy for what AI applications some of them might be promising, but at the same time, there's a danger if they aren't designed very carefully. So it's useful. Another historic point that I want to make about the context here relates to my discipline. I'm a statistician, and David Gresham mentioned some of these points when he was talking about the history of the concept of race in science. And I think he also pointed out in one of the readings that some of the founders and most famous statisticians of the 20th century were also really kind of virulently racist eugenicists. And that's a fact about my discipline. That's a fact that it's still reckoning with today. And, before the advent of computerized, high-tech AI applications, when statistics were more simple and the kinds of data that we had were more simple, we already had problems with the way that data was being used. So, very early on earlier in the 20th century, the US Census Bureau actually used census data to assist with the internment of Japanese Americans during World War II. So data can be used for bad things. That's not a new fact. That's something we have to remember from history, and remember that AI doesn't change that fact. So another thing that's sort of new is this recent wave of research in AI, I think also kind of grabbed a lot more of attention. And people started paying attention to some of the potential problems that can occur. So we started seeing more research in academia, where people who had previously been working on machine learning, um, the new hyped kind of methods of deep learning were becoming very famous around 2016, and a lot of people were starting to do research on those topics. And I think at the same time, a lot of people were also noticing the social impact that some of these new systems were having. And there was a book that kind of became somewhat of a bestseller and well known in the public from 2016 that drew attention to the use of data and algorithms in many different areas of life, like college admissions, employment, and healthcare, and pointed out that there are kind of new dangers associated with the way that we're using data. So it's true that there is a historical continuity, but it's also true that there are some things that are new. And some of the new things that are important to pay attention to are things like scale. So the technological improvements mean that we have more data, we have faster algorithms, we can just do more things using data and apply that to more areas. Also, these algorithms can be opaque, they can be hard to understand, as I've mentioned. And another potential new problem here is that sometimes people have a naive view of these technologies where they think that because it's a computer algorithm, it's objective in some sense. Um, this is not, a computer algorithm is, again, just a tool created by humans and used by humans. But this is a sort of, I think because it's somewhat opaque, people then tend to think it must be correct. Someone who understands a lot of math and computer engineering designed it, so it must be technically correct. So these are some of the new risks that people started noticing around this time. And some of these risks we started to see examples of in the news. So I think another sort of fact about the current academic setting, like how I came to work on this, is that around 2016, when that book came out and some other academics started working on this area, there was also a lot more journalistic attention to some examples where it seemed like algorithms were going wrong in some public application. So here's an example where this shows how there's some risks associated with opacity, with the fact that these algorithms are complicated and we can't really see and understand all of their inner workings. So Amazon was trying to create an AI that would be able to automatically scan through people's resumes or applications and sort candidates for job applications and decide who, for example, it might decide who should be interviewed by a human. And Amazon found that this algorithm, this AI that it had created, was penalizing candidates who are women, including when they found some ways of auditing the inner workings, like looking at exactly what the algorithm was doing. For example, you could create a resume and just change one word in it and then input that into the algorithm and see if the output changes. And if you do something like that, you can see how the algorithm responds to the presence of that one word. And with that method, you could find, for example, that the AI was penalizing just the word women's. So if someone was a member of a women's club of some sort and had that on their resume, they would be penalized for that. So if the workers at Amazon had not audited this AI and checked and found that fact, they could have possibly put this, into production, and then this AI could have been used to actually screen applicants and it might have had some important real-world impacts. So when we have simpler models, it's easier for us to look and see if it's doing things like this. When we have more complex models like AI, it's harder for us to discover issues like this issue here. It's one of the reasons why I've kind of belabored a little bit the historical continuity of AI technology with previous technologies that we already knew have been used in problematic ways, is that there's a surprisingly persistent and fairly popular idea of progress and technological solutions, where a lot of people tend to believe that algorithms cannot be biased because they're just math, and math is objective, so it can't be biased. I'm not sure. I'll kind of skip past this a little bit. I would just question whether it's true that algorithms were not politicized before researchers started paying attention to their bias. I think all technology is developed in a certain political context. So here's a few more classic examples of algorithms so that we can contrast what modern examples do. These are, I think of these as kind of the two best examples of classic regression, a linear regression, and a decision tree of methods that humans can understand. These are relatively easier for us to understand what the algorithm is doing. With decision trees, there's just a list of rules, and you can just read down the list and check the criteria and understand how the algorithm reaches its decision. So for example, this is a decision tree which I currently am paying a lot of attention to because it means that I can't get the vaccine yet here in the UK. But I can see that, I can understand exactly which variables about me are being used and how they're being used. And then regression is similar. Here, instead of a sequence of decisions, there's just a formula that adds up my different variables and gives them different weights. So if I want to know how the algorithm treats me and how my variables are used, I can look at the weights for those variables. So these are methods that we've used a lot, for a century now almost, and they're useful for understanding how AI is very different because we don't get this type of interpretation with AI. In contrast, so this diagram on the right is showing an actually simplified version of a deep neural network, which is kind of the current state of the art for what AI models are based on. And in this, the thing to know about this diagram is that the left-hand side shows predictor variables that are input, and then the right-hand side is the output. And then in between are various functions all being composed with each other. So if I wanted to know how one predictor variable is being used, I can no longer do something like look at one coefficient in a linear model. I would now have to trace this one variable through this network of many different functions, and these functions are also nonlinear. So it's now very difficult to understand how my output depended on the value of one of my predictor variables. And this is actually a relatively simple example of a deep neural network. The kinds that are typically used in some of these examples from tech companies can be far larger and more complicated than this one. So you can kind of see how it's harder to interpret these methods. It's harder to understand how the algorithm is reaching a decision about a given person. And that's an important fact when we want to understand if the algorithm is treating people unfairly, if it's being racist, for example. So this is a example showing kind of the increase of complexity of models over time. So when we first started using regression, we had models with a very small number of parameters, a very small number of coefficients. About 20 years ago, it was common in scientific publications, at least, to use models that had on the order of thousands of parameters. So already it's very hard to understand the kinds of models that people are using 20 years ago. Now we're in state-of-the-art AI applications. There are models that have billions. Even more recently, there's a model that has over 1 trillion parameters. So it's now basically impossible for humans to understand the entirety of that model and how it forms its predictions. So we really have to sort of focus on the output. What happens with the output of the model? Let me skip this and just emphasize that we can now check the outputs of these models. And that connects us to the legal frameworks in the US regarding discrimination. So there are notions of disparate impact in US labor law that say that if we use a rule, for example, for hiring, and if that rule results in differences of hiring rates, so the outcome, the impact of this rule results in discrimination, then it's possible that would be illegal. There would be a court case to decide if the use of that rule is allowed. A company would be allowed to try to defend its practice. It could try to prove that it needs to use that rule for its business purposes. And if it could not prove that that rule is necessary for its business purposes, it's just a rule that resulted in different outcomes, then it would be considered illegal. So this is a sort of legal framework. It's about hiring and labor. It's not about AI. There's almost no laws on the books directly about regulating these technologies yet. So people are trying to connect them to some of the existing laws from contexts where they might be used, like that Amazon application might be used for hiring. And then you could see, even if the Amazon's AI is too complex for us to understand what it is doing internally, we could see who it's hiring, and we could see if there's differences in the rates of who it's hiring, and we could possibly understand if there are disparate impacts of that algorithm. So this is kind of one of our main tools we can use for trying to audit these systems. We can look at the output and see what it's doing. It's a lot more difficult to understand how the algorithm is treating a given individual person, how it's using their specific variables, because it's such a complex algorithm. So I'm going to now switch to covering several examples. And the first example we'll see here is also image related. That's kind of again, images are like the kinds of AI applications that get a lot of attention because it's easy to look at pictures instead of tables of numbers. So this is from the Gender Shades project, which is a really interesting, important work where they found, they created a benchmark data set using images. I believe these are images from members of parliament in different countries. And they created this data set, and they wanted to use this data set as this sort of outcome test for various AIs. So you take this, the idea is you take this data set, you have access to some AI, so you can ask the AI, what is the output for this image? What's the output for this image? And so on. And then you could, for example, check for disparate rates of how what the algorithm's outputs are on the basis of the kinds of variables that you might know about these individuals, to check to see if there's if the algorithms are discriminating in the sense of disparate impact. So that's what they did with this project. And they found for several facial recognition algorithms from some pretty large tech companies, that the error rates in outputting the gender of the person in the picture, so that's the output that they were asking for, the error rates were different between different groups. And in particular, the accuracy was much lower for dark-skinned women than for any other group. So there's this is a disparate impact. If this algorithms are being used for gender classification in some application that has other important consequences, decisions are being made based on the outputs of this algorithm, then that could potentially result in discrimination. So after this paper was published, these companies responded by basically they created more data sets that would allow them to increase the accuracy of their AI on different subgroups. So this was a very impactful paper. It got a lot of people's attention, and the companies responded very quickly. Okay, so I'm now going to talk about several more examples and emphasize some specific aspects of each of them. These are not necessarily aspects that are new to AI, but these are aspects that I believe are important to understand. So some of them might be new, others of them might just be things that are common between AI and regression, but are still some of the most important consequential things. So let me pause here really quickly to see if there's any questions, quick questions so far.
You can raise your hand or type in the chat. It doesn't look like. Oh, there's one question. Gino, go ahead.
Hi, about this factor you just discussed, like the bias given to the data. There was a recent debate about this, like a few months ago, related exactly to this point. Some AI algorithm were biased towards a specific gender or a specific race, a specific face or whatever. And some experts said, in the AI field, even in face recognition, said, well, this is purely due to the fact that the data set, the input data set, the learning data set is biased. So if you have a 70%, 30%, between male and female, you will get that as an output. And I don't know, to me, that didn't really seem a convincing argument. And some people were opposing this. So my question is the bias only related to the unbiased in the input data set, or there is something more?
Yeah, that's this is a very commonly discussed question because I think there's a reason for it. If I try to be somewhat empathetic and understand the viewpoint where some of these people are coming from, I think that some of these people are researchers or engineers who have worked, for many years. Maybe they've spent their entire careers doing something, and it's kind of difficult for them to cope with the idea that some of the things that they've worked on could be harmful in a way that they could have potentially been responsible for. So it's important to have some type of rationalization that says there's no way I could have been responsible for this. See, I only work on algorithms. I don't collect the data. So it's easier for me to believe that this bias only comes from data. It can't come from algorithms. So I think that's the reason why this idea keeps coming back. And I don't think the idea is mathematically, statistically, philosophically, scientifically interesting or defensible. It just keeps coming back because it's useful as a rationalization. There isn't really a way of distinguishing between what is the algorithm and what is the data when the algorithm takes data as in machine learning, right? So any fitted machine learning model or AI has data as one of its components. It depends on the data set. So yeah, I mean, if we're talking about the idea, the notion that like a mathematical operation itself, like the just addition, adding numbers, if we're talking about algorithms on that level, sort of almost a Platonic description of what an algorithm is, then maybe there's a little bit of merit to this argument. But as long as we're talking about any of the algorithms that are actually being used in the real world, we're so far from that being the relevant description of what the algorithm is that I don't find that a useful discussion to spend more time on. It's a good question. I don't mean to say it's not a good question, but I would just say, let's move on from it in terms of whether the bias comes from the algorithm or the data. Let's just agree that there is a bias and we've got to figure out how to fix it. Okay.
Sorry, there's one more.
Go ahead.
Question, which is, how was the Amazon AI trained?
Good question. I don't know any more of the specifics about that example. I'm sorry. So I don't know the that Amazon AI. Okay, so I'll pause again quickly after this section for more questions, and we'll have questions again at the end. But let's talk about a few more examples of biases. And so I'll talk about several different examples here in several different categories of applications, like health, policing, commerce, and labor. And these are some themes that I would like to pay attention to, and I'd like to draw your attention to. So issues of sampling bias and feedback. Now, that's not a new thing related to AI. These are classic statistical problems, sampling bias, but I think they're still one of the important facts we always need to remember that still apply to AI. Optimizing for the wrong thing. Now, that's a very AI specific. In AI, when you're fitting AI, you use really powerful optimization algorithms. So whatever you're optimizing for, you end up with a program that is really focused on that one specific thing. And this can come at the detriment of any other kinds of goals or objectives. So that is kind of a unique AI problem. And then opacity, high dimensionality, sort of the complexity of the models, combined with structural racism and causation. This is another specific category of problems that we'll come to, and then responsibility. I'll just point out how each of these themes relate to some of the examples as I go through them. So let's talk about this health example. This is from a paper from 2019 that studied a bunch of an AI system that is used in hospitals. It was actually being used by a hospital network. So I think there were actually like many hospitals that were using this. And it's an algorithm that's supposed to do something like triage. So it's supposed to figure out which patients need additional attention and care. So the idea here is that this algorithm is taking as input the patient healthcare records, and it's going to use them to figure out which patients are at a high risk. So in order to direct attention, so like who should a nurse talk to, who should a doctor talk to. And the way that they trained this algorithm was to predict healthcare costs using patient records as predictors. So the output, the thing that they were optimizing for, predicting, was healthcare costs. Now, if you think about this for a minute, there's a logic to that that makes sense. If you want to know if patients are going to require more care, it's kind of difficult to think of all of the different types of health complications that could happen as different possible outcomes, and to sort of also normalize them by how severe they are. It would be a very complex task to figure out how to come up with one specific outcome that encodes on some scale if someone is at a higher risk of developing a more severe condition. But what you could do very easily, because you have this data, is use the cost of how many, what is the cost of all the procedures that a given patient has had? The idea being, if they have much higher costs, then they probably had more conditions, more severe conditions, and so on. So basically, this is doing something kind of economics. It's using a price signal here in order to come up with one outcome variable in order to avoid the kind of difficulty of figuring out how to predict all the different possible health conditions that can occur in a hospital. So that would be, I would think, the reason why someone would design a system using the cost as the outcome, why it might make sense. Another reason why it might make sense is the incentive. The hospital might want to know which patients they'll be able to charge their insurance companies more for. So I'm not sure which of these reasons, but at any rate, they had an algorithm that predicted healthcare costs. And from that, using healthcare costs as the outcome, they would decide who is at higher or lower risk. Now, what the researchers in this paper found when they analyzed this algorithm that hospitals were already using, they found that this algorithm was underestimating risk of health conditions for Black patients compared to white patients. And this plot is showing this systematic underestimation. So the horizontal axis is the algorithm's prediction of risk. And then the vertical axis is the number of active chronic conditions for patients who had that predicted risk from the algorithm. And so you can see that Black patients tended to have more active chronic conditions at the same algorithmic predicted risk level as white patients. And the researchers also found that if they just adjusted the algorithm, so they used this information to close the gap between these curves in some way, that a corrected algorithm would have resulted in 2.5 times more of the Black patients being categorized as needing more care and receiving more care than they were under the baseline. So there's several interesting things about this example. So let's kind of revisit a few of these concepts that I'm trying to organize the examples around. Actually, so one of them is optimizing for the wrong outcome. They're predicting healthcare costs rather than actual health conditions. Another one is responsibility. So whose responsibility is it to change this? How do we go about changing this? Do we just tweak the algorithm? If we just tweak the algorithm, that might actually result in Black patients receiving more care. And I think that last fact also shows why there is, for some people, there is a sort of a promise to this idea that there might be simple solutions that we can implement really quickly. Whenever we find examples like this, it means that there's some algorithm and we just have to change the way the algorithm works, and then that will make the world better. So there's some appeal to this idea that there will be fast and simple solutions. I'll come back to this idea. I'm not so sure that I'm not so confident that those solutions will work. Another healthcare example, this is more of a thought experiment here. And I'm going to introduce a little notation here related to causality. We've seen some examples related to genomics and healthcare studies. David Gresham and others have talked about the biased samples in a lot of health research. And so it's possible that a lot of genomic healthcare research is based on samples that don't have a lot of racial diversity. And that is one kind of risk and one kind of problem and way that that resulting research could end up being biased. But I want to talk about a different possible risk here. And the risk, this one is something that I think of as sort of the problem that's also underlying racist applications of behavioral genomics. So some of the things that we've also heard examples mentioned before about trying to do things like correlate IQ with genetics. So here you could try to correlate a health outcome, and your goal, you might actually, have the best intentions, where your goal is to be able to use genomic data to predict risk for different health outcomes in order to, give the best treatment to different people. Now, the problem, here's what I think could possibly be a problem with this approach. This diagram here shows a sort of toy example of the world where each variable causes the variable that is in the graph with the arrow directed away from it. So here, Y is some health outcome variable we're studying. S represents structural racism. We may not actually be able to observe that in our data set. So this is a model of the world, not a model for what data we have. But structural racism could certainly influence health outcomes. We know, for example, there's more pollution in affecting communities where there are more Black members. And so we know that that can affect a health outcome. And then it could also be true that genomics is correlated with race for reasons having to do with, superficial traits like skin color. We know that the racial categorizations are not scientific classification systems, but there might be some of these weak correlations, population level correlations between traits that were selected for like skin color. So as a result, because the health outcome here has been affected by structural racism, which also correlates with race, and because there are some genomic markers that also could correlate with race, it's possible that you can predict the health outcome using genomic markers. Now, the problem here is that in this toy example, again, this is just a toy example. It's not necessarily, I'm not saying that there's any health outcomes that actually work this way, but in this toy example, the health outcome is not caused by any genomic factors. It's totally unrelated to genomic factors. So if you can predict it using genomic factors, that's only because of correlations with other variables, not because genomics was an actual direct cause of the health outcome. Okay, so if there are examples like this, and that's a big if because it's a very simple toy model, but if there are, then there's greater risk when we use AI-like methods, when we use complex predictive models that have high dimensional data and use very complicated prediction rules. These machine learning tools and AI tools can search through data like that to find correlations. And so we might be able to find correlations that can predict health outcomes using genomics. Now, why would this possibly be a risk? This could be a risk if our resulting conclusions are that, for example, that different populations have higher risks for health conditions because of genetic causes, right? So here, if that's not true, if the health outcome is caused by factors associated with structural racism, then we've identified the wrong cause for the health outcomes, and we would pursue the wrong courses of actions in trying to remedy those health outcomes. This risk is greater because of the complexity of the kinds of models that we're using when we're searching through these high dimensional data sets. Okay, so brief recap of these health AI applications. The first one was definitely optimizing for the wrong thing, cost. There's a sampling bias where it's probably the case that more of the Black patients had less healthcare costs in the past because they had less access to healthcare in the past, not because they actually had less need or demand for healthcare. And we also saw the potential risks in AI applications that are kind of uniquely connected to dimensionality and causation. Now, let me go relatively quickly through some of these other applications. They're kind of going to reiterate a couple of these key risks. So here's an example from, this example became very well known because of ProPublica's reporting on an algorithm that was supposed to predict risk scores for criminal recidivism that would be used at pretrial court cases to decide if someone could be allowed to post bail or would be detained without being allowed to post bail on the basis of the risk score, which is output from this algorithm. And ProPublica did an analysis which found that they did an output type of analysis here, and they found that these scores were biased against Black defendants. So there is a hope that using algorithms like this would be able to, I guess, make the court system more efficient in some sense, that would be able to allow, the idea is if the algorithm is more accurate, it would be able to actually allow fewer people to be detained. And so there was actually some reform efforts in California. There was a ballot measure that would have abolished California's cash bail system, but at the same time, it would have used one of these algorithmic systems to predict risk of recidivism. And this proposition failed. I'm thinking it failed for multiple reasons. One, because there are problems with algorithms like this, so some people opposed it for that reason, but another probably also because the bail industry opposed it. I think it's not clear that many voters understood what the algorithms would do, because the algorithms, many of them are proprietary. We don't know what they do. We don't have the code for how the algorithm works. And so, for example, if the algorithm uses something like prior convictions as one of its measures of an input to decide on risk, then even if the algorithm does not use race directly, it's possible in an unfair world that race combined with structural racism has resulted in more previous arrests for marijuana, for example, which therefore also resulted in more prior convictions. So even if the algorithm does not explicitly use the race variable, it just uses the prior convictions variable, this potential correlation could mean that the algorithm is unfair. And in fact, that is probably a realistic idea for what's happening in the world. This is from a study where researchers compared arrests for drug use to healthcare data on drug use. So arrest data is very biased. You only observe arrests where there are police. Healthcare data is a little less biased, because if someone is having an emergency related to drugs, they'll call the hospital even if they would be too hesitant to call the police. So this graph here is showing drug use. You can see that it's spread pretty much everywhere. This graph is showing drug arrests. The drug arrests are concentrated in neighborhoods in Oakland that are predominantly Black. So this is an analysis of a predictive policing algorithm system that found basically you have this feedback problem. The training data comes from an unfair world. And so it will come up with unfair predictions. And if police go back to the same locations, that will just result in more unfair training data for the next iteration of the system. Okay. And then I know I'm almost beyond time here, so let me really quickly wrap up the last examples. This is an example showing where Amazon Prime had same-day delivery available. It was they made same-day delivery available based on where they had more customers who were signed up for the Prime service, I guess. And that's the left-hand plot here. It shows you where the same-day delivery was available in Atlanta. The right-hand plot here is showing the redlining maps, where Atlanta was deliberately discriminated and segregated for housing mortgage rates and housing purchases. And the point here is that there's this unfairness from decades and decades ago that still persists in kind of unrelated systems now, systems that tech companies are using. And there's a question here of who is supposed to be responsible for remedying this disparity. I think after this was reported, I think Amazon did expand its same-day delivery area. But then when we're talking about responsibility for that as well, then there's further issues like the laborers themselves who have to do same-day delivery. So a lot of times with AI systems, another one of the high-level points I'd like to make is that a lot of times with these AI systems, they're kind of assigning responsibility to others, people who are not the company designing the AI. So this is an example related to the delivery drivers. When these systems are optimizing for something like fast deliveries, they have outsourced the risks to the drivers to figure out how to get places faster. And an AI doesn't know anything about this. It just knows how fast a delivery happened. It doesn't know which roads are safe or unsafe. Those are not being input into the AI, at least in its current form. Let me conclude very quickly by some of the ways that I think are useful for trying to change these problems. The good news is that some of these things are already happening. So there's inclusion in terms of the people who are working in AI, regulations, and attempts to democratize data. So there are organizations like Black in AI that were founded fairly recently that are helping to improve the inclusion with the problem of sort of non-diverse workforce in the tech sector and in academia and people who are working on these problems. So I think this is one reason to be somewhat more hopeful that we're going to have a more inclusive community of people working on these problems. But it is taking time. There are obstacles. There was the recent example of Google firing AI ethics researchers. So it's not easy. And this is something that I hope I can, I hope that all of us who are advising students can make our own efforts into helping with this part of the problem. There's regulations, which we're starting to see, especially in the EU. And there's a lot of support for more regulations, both in the public and among tech workers. So there might be some reason for some optimism there. There might be some improvement there. I think regulations are a necessary but not sufficient step because regulations are a tool that comes with their own limitations. And lastly, democratizing data is another interesting thing that's not just trying to regulate how companies are using data, but also using the government, which we have some democratic control over, to create new forms of collecting and using data. So you can think, for example, about the fact that we already have some information infrastructure, public information infrastructure, like libraries. And you can imagine trying to create the new versions of libraries for the internet era. We can imagine things like having a public option for internet, a public option for cellular data, and other sort of democratically controlled means of changing what data exists so that the data that's being created is not all about targeting ads, but about doing other things as well. Some things that might be socially beneficial in other ways. And then in conclusion, I just want to end with a little bit of statistical wisdom here from George Box. George Box is talking about statistical models, but what he's saying is also true about any kind of AI application. He said that all models are wrong, but some are useful. And we have to be alert to what's importantly wrong about them. So I would just add to this that when we're talking about what's useful and what's important, we should also add the questions useful to who and for what, and what's important to who and for what. And probably one of the most important things that we can do with AI applications is to figure out how we can change the objectives that we are optimizing for. That's probably one of the most high leverage things that we could focus on if we have the ability to change, if it does come down to us individually to make that choice, if we're designing this, if we're working at a place, at a tech company, and we along with some of our coworkers might be able to influence some of these choices. Changing the objective function is probably one of the most important ways that we can avoid some of these problems. Okay, so I forgot to stop to ask questions earlier, but I'm done now, so we'll do all the questions now.
Thank you so much, Josh. Yes, if you have a question, please raise your hand or type in the chat. I'm going to start with one question. So you said earlier that sort of a quick and easy fix for predicting the healthcare outcomes and the gap between fixing the gap between black and white patients was not necessarily something you would believe in. Could you elaborate a little bit more on that?
Yeah, so I guess, so on the one hand, it's a very simple reason to be optimistic about, or to be skeptical about something, is how easy of a solution it seems to be. So if there really is a solution that's that easy and that would actually work, then someone should have done it already. It's possible it will work. I mean, it's possible it was just overlooked, and that making that one tweak will actually make a big difference. And from that point on, things will be better. Another reason why I have to be skeptical about it is all of these systems, AI systems, are socially embedded. And so if you change something about the AI, it's possible that the way the AI is being used by the institution will also change. It's possible that other actors, other decision makers will also change their behavior. So another example of this could be with attempts to reform policing. For example, the NYPD stop and frisk program was eventually officially terminated as a result of at least partially as a result of some data analyses of the data that was collected, because there was a law passed requiring the police to fill out a certain form whenever they stopped someone. And so there was all of this data from this because of this law that passed. So on the one hand, so there was this change, like make a law to collect some data. There's now going to be some evidence that can be used. But it's probably also true that police would change their own behavior in response to this requirement. So, they might change the way they fill out these forms. They might change the way they're deciding whether or not they want to stop somebody. So at a higher level, aside from healthcare or policing, just in general, when you have a system that involves people making choices based on how the system works, if you change the way the system works, then people might also change the way that they're interacting with it.
Thank you. More questions. So one theme that I found recurring in your talk was the importance or the fact that lots of people seem to be outsourcing responsibility. Like companies do that, individuals do that, especially if you're on the technical side, you say, oh, this is not my issue. It could be out of ignorance or out of ideology. What systemic fixes are needed there?
That's a tough one, but I think actually there's something specific I can say about this. There's this essay, I think it's a classic essay by the statistician Erwin Bross, who wrote, he wrote something like, statistician, if you're a statistician or you're a data analyst, you have to decide if you, and his phrase was, if you want to be a scientist or a shoe clerk. And I hope there's no kind of like moral judgment about either of these titles, but the idea is, on the one hand, like what you do if your job is to sell something to someone is you find the version of the product that they would like best. So, if you're working as a data scientist and you're working at some company, they've asked you to do something, you have managers who are interested in their quarterly performance metrics. There is a way that you can try to do your task with the best possible quality and scientific integrity and so on. And then, that might run contrary to what your manager wants, for example. And so you have to face this choice as an individual data analyst, data scientist, or worker between, and Erwin Bross was thinking just from a scientific perspective. So either do you pursue the truth, or, we could add other objectives to this as well. It doesn't have to be science necessarily. So could you pursue a more socially positive version of the work that you do at your company, or do you compromise because of this pressure? And one of Bross's points was that we kind of need professional organizations to protect individual workers when they make the choice to follow their conscience. So when they decide that it's wrong to compromise their analysis in a certain way because it's what the company wants, because it's more in line with the profit motives at that time, and so on. So this is actually a really important, I think this is a really important factor in statistics, why statisticians as a discipline have some amount of prestige and responsibility and involvement in regulatory agencies and so on. I think it's partially because people think of statisticians as trustworthy because they're a little more extreme in the direction of not wanting to compromise the scientific integrity. But so, okay, then I think that this is one thing that we could do to try to help with this problem is we can try to have some types of professional organizations that can protect individual workers when individual workers want to say, become a whistleblower about the fact that the tech company that they work at has an algorithm that's doing something harmful, for example.